Hello all, welcome to my YouTube channel. So in the last video we have plotted VTC curve for a CMOS inverter, and in this video we are going to see that when is the power dissipated in a CMOS inverter observed. So let us start by creating a new schematic in LTspice. To make a CMOS inverter we will require an NMOS as well as a PMOS. Okay, like this we will take one NMOS and a PMOS device, both operating in the complementary mode. We will require two voltage sources. The first voltage source is the VDD and the second voltage source is going to be your input voltage. Since it is a CMOS inverter, the same voltage will act as an input for both NMOS and PMOS and will be supplied to the gate terminals. The body terminal of a PMOS will be connected to VDD and that of NMOS will be connected to the ground, like this, and we will provide the ground here. Okay, so let us take ground and provide it to both the voltage sources as well as NMOS and take the output from this terminal. Let us take VDD as 5 volts, input voltage also as 5 volts. For PMOS I am taking length as 100 micro, width as 10 micro, so that the W by L ratio for a PMOS is 0.1. Similarly for NMOS I am taking length as 400 micro, width as 100 micro, so that the W by L ratio for NMOS is 0.25. To make it visible, press Ctrl key from your keyboard and right click your mouse. Okay, and now you can see W by L ratio for both NMOS and PMOS. The next step is to include the model file. So I have already taken the model file. I will just copy it and in the spice directive I will paste it. This is the model file for NMOS. Similarly, I will take the model file for PMOS. I will copy it and in the spice directive I will paste it. How to include the model file? I have already made a separate video for it. You can check it out on my channel. For the threshold voltage of PMOS I will take as -1, and for NMOS the threshold voltage I will take as +1. And click on OK. The last step is to edit the simulation command. I will take the DC sweep, and since it is a VTC curve on the x-axis I will require the input voltage, which is V2 in this case. Type of sweep is linear. It should go from 0 to 5 with an increment of 0.1. And finally let us run it. Tile the window vertically and observe the VTC curve first of all. This is the VTC curve that is observed, where this is point A. Point A is the one at which NMOS is in cutoff, PMOS is in linear. This is the point B at which NMOS will be in saturation. This is the point C in which both NMOS and PMOS are in saturation. This is point D where PMOS is in saturation, and this is the point E in which NMOS will be in linear and PMOS will be in cutoff. So to observe the power that is dissipated in a CMOS inverter, let us find the current that is being drawn from the power source, because then the since power is equals to V into I, so the portion of the graph at which both V and I will overlap will give us the power that is being dissipated in the CMOS inverter. So first of all let us check the voltage here, that is the input voltage. This blue line represents input voltage and this is the point where Vin is equals to Vth. Okay. To observe the current, place the black pen here. Okay. So you can see from this graph that the current that is being drawn from the power source is maximum during the transition. Okay, during this transition. And what is this transition representing? This is that portion of the graph at which both NMOS and PMOS are working in saturation. So we can conclude that the we can conclude that the maximum current that is being drawn from the power source occurs when both the transistors are operating in the saturation mode, and this is the only region in the CMOS inverter when the power is being dissipated. Rest, the current that is being drawn from the power source is zero. So in a CMOS inverter, the power dissipation occurs when V input is equals to V threshold, and during the transition at which both NMOS and PMOS are operating in the saturation region. So if you have any queries regarding the same, you can ask in the comment section below. Thank you.